So here we are, boys and girls. We're looking at, some of my little treasures. This is a carving, and I think it's marvelous. Uh, and it's a diamond, diamond. Right. It's not one of those perfect diamonds that De Beers sells you, and there's some flaws onto the surface there. There are planes of cleavage that I talk about, and that's what you see in there. They're under the surface of the stone. And it's not broken, it's just a little discontinuity. The atoms all line up in perfect little rows and columns. And they are not perfect right there. And so here's one that is perfect. And it is so perfect you can see the z-axis going down the middle. It's normally a kind of a guess where the darn thing is. In this case, this crystal is so perfect that the X and Y axis, and when I got this crystal, it was all rough on the edges, around the edges, and on the apices, the corners. So what you're seeing is the X and Y axis of those planes of cleavage. And it is so absolutely perfect in this stone that you can see the z-axis where they come together. And that's not like glued together or something. That's the way the natural crystal formed. I got this in with other natural crystals of diamond out of Brazil. And it makes little prisms, right? Little three-sided prisms, 4 of them, around the z-axis. So when I go like this is not a rainbow diamond. It's just a clear diamond, but it makes rainbow colors because like doing the prism thing. And if you look like this, you'll see that it makes a perfect tesseract. There's a cube within the cube. That's what is proposed as 4-dimensional space. And there it is inside my perfect diamond crystal. Device too hot. All right, so there it is, and that's my bid at perfection. Very few things are perfect, but this one is. And I want you to notice something about this cube. It's cube. How many sides do you see here? 1, 2, 3, 4, 5, 6. Because I'm looking at it from 45 degrees. Okay? So cubic and hexagonal are part of the same system. A lot of what people call quartz is not quartz at all. And the structure of quartz, as given in geology books, is a silicon atom surrounded by 4 oxygen atoms. Um, okay, so if I put a silicon atom in the middle of that, right in the middle here, right where my fingernails touching the middle of that line there, and I put 4 things around it, it doesn't fill all the spaces because there's 6 sides, not 4 sides, to a 3-dimensional object. Only 2-dimensional objects have 4 sides, so if I put it here, it 1, 2, 3, 4, but it's if I do 1, 2, 3, 4 this way, I get a plane 1, 2, 3, 4, and it would be like one of those planes inside here. So in order to have a 3-dimensional object, you gotta have 6 sides. I mean, 6. Yeah, they attach in 6 places. And the bond angle of what they call quartz is 144 degrees. Okay, and that means that all of the internal angles within the quartz crystal would be predicated on a 144-degree bond angle between the oxygens and the silicon. That's how crystallization works, okay? And in this case, the atoms of carbon all are the same size, and they line up in perfect rows and columns. So they form planes of cleavage, and you can see it on the sides of the crystal. And in fact, if you don't see those on the outside of a crystal, it's probably not a diamond, because they all have them. And if I shave that off and polish it perfectly, I can blow it up, and you'll still see the rows and columns because they are so much a part of the structure of the crystal. Okay, so if a crystal had hexagonal symmetry, it would have 6 sides. But hexagonal also means either one long axis or one short axis. So not 3 even axes. Cubic means 3 even axes. So 1, 2, and 3. Okay. But cubic and hexagonal are the same thing. It just depends on which way you look at it. Wow, huh? That's kind of confusing because it's, actually real mathematics and not just make-believe, and that's what we call the cubic hexagonal system. And they're the same system. It just depends on which way you're looking at it. I have hexagonal crystals, like rubies and sapphires, that are perfectly, they've got 6 sides that are perfectly even. And they're little short crystals, little short fat crystals. Or sometimes a long barrel-shaped crystal. They are not cubes. They are not ever cubes. And crystallization is how one of the ways you tell what something is. Okay? Diamonds will glow in all wavelengths. Uh-oh. There's one wavelength, red. Okay? And we go to the other end of the spectrum. It glows in blue. So, and that's what that is too. And they're not little because they came out of the fault line. They're not kimberlite diamonds. They're fault line diamonds. And they're not rare or hard to find because every river, creek, and dry wash in the world follows a fault line. And I didn't make that up. That's what they are. And they connect not just to each other, but all the way down to the semi-molten mantle, 55 to 75 kilometers below your feet. Kimberlite pipes are caused from asteroid strikes. Okay? So when it hits, boom, it vaporizes the surface minerals and they recondense. And that's why my kimberlite diamonds are so small, because they're just little bits and pieces of things that were started out as calcite or fluoride or something like that. And the cubic structure is generally more like the diamond shaped. So it would be more like that. And that's what causes that shape. And so the structure tells you the environment too. In a fault line, these come up slowly and they cool slowly. And you get much larger crystals because there's more stuff as they're growing. Whereas with a kimberlite pipe, it's just a quick and brief melt and recondenses almost right away. So that's the difference. Now the other thing, of course, is that when the carbon is coming up, the depth of formation determines the color. So the deepest ones are these purple ones. They are the closest, the planes of cleavage are the closest together. And the ones that are furthest apart are clear ones. And it ranges, purple, blue, green, orange, yellow, red, or yellow, orange, red, I guess, pink. And that those are found more often in fault lines rather than kimberlite pipes, because kimberlite pipes aren't deep enough. Okay? Now, one of the things with this is that these are all the same hardness, so I can't scratch this one or this one. Didn't actually scratch it. You see what I mean? What happened is this is rougher than the little sharp edge here, and it took off some of the little sharp edge. It's acting as an abrasive. A scratch. I did it across that line there. And there's no scratches that way because they're the same hardness. And they're all 10 on the Mohs scale of hardness. It's the hardest thing on the planet. And about 100,000 times harder than the nearest contender, which is rubies and sapphires. So, and I know about these things because I didn't just read them in a book. I checked more than once, like tens of thousands of times. And you can too, because this doesn't require, doing a scratch from one crystal to another. Does not require any fancy equipment or information you don't have. That's how you do field testing in geology. Peace, y'all.